11.5, intensity. The intensity of a wave. So the intensity is the radiant power passing through a surface per unit area. It's power divided by area. So it's watts per meter squared. Radiant, in this case, means transmitted by radiation. It means radiating. So this is what waves do, they radiate. Now, from a point source, like a light bulb or a star, the energy radiates into three-dimensional space, and so the surface area is spherical, isn't it? And the surface area of a sphere is 4 pi r squared, and so in place of A we have 4 pi r squared. R is the radius of the sphere, or in other words the distance from the point source to the point where we want to measure the intensity, okay, given a certain power output of the point source. Let's do the sun. Take the sun as an example. The power of the sun, well, let's look at R. The distance is 150 times 10 to the 9 meters. The power of the sun reaching the earth over a meter squared is every meter squared of the surface of the earth receives about 1400 watts of power from the sun. Okay, so if we rearrange the equation for power, we get intensity times 4 pi r squared. What we've done here is just we want to rearrange this for, we just multiply both sides by A, don't we? Power equals IA. A is for 4 pi r squared. Put the numbers in. 1400 times 4 pi times r squared gives us a massive 4 times 10 to the 26 watts. That's the power output of the sun. Every second the sun is producing 4 times 10 to the 26 joules of energy. That is a lot of energy during this video. Can you see how the power reduces by a factor of 4 if you double r, the distance from the point source? Here's my natty drawing. Let's zoom in. Like it. So look. Here's the sun. Here's us receiving it on Earth. Let's say Earth is a little dot just there, you see. Well, I mean, forget that analogy. Let's just go for the whole thing. So look, the sun radiates its energy through a sphere at a distance r. Here's a window that I've cut into the sphere, and it's got this surface area like that, right? Now, if I double r, if I double the distance to here, can you see how this surface area expands out to 4 times that surface area? We may have mentioned this before, I can't remember. But you double these distances and can you see how that area is the same as that one there that I've marked out? And the same as this, if my drawing was good enough, and the same as that, same as that. 4 times the area. So if you double r, you increase the area that the power is spread over by a factor of 4, and therefore the intensity reduces by a factor of 4. Double r, so power is directly proportional to r squared. If you double r, so from 1 to 2, 1 squared is 1, 2 squared is 4, 3 squared is 9. So if you go out a further r, you're going to get 9 times the surface area. We'll get 9 eventually, won't we? You see, like that. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I was to continue the drawing. Beautiful. Now, over here, let's just talk about what happens to the intensity when the amplitude of the wave decreases. Now, we have actually the intensity is directly proportional to the square of the amplitude. If you double the amplitude of the wave, you're going to increase the intensity of it by a factor of 4. How? How is that so? How is it true? How can we understand it? Let's have a look. As a circular wavefront spreads out, its intensity reduces. The amplitude of the oscillations of the particles on the wave reduces, right? Here it is. Look, I've drawn it over time. Boom, look, gradually. The amplitude gets less because the energy is spreading out. So let's say the amplitude halves. So where have I got half? See, that third crest is about half the amplitude of the first crest, right? So look, if you're a particle in this first crest, you've got to go, let's go down, up and down and up and down and up and down. And here you're going up and down and up and down. For the same frequency, we're going more slowly, aren't we? Yeah, that's a slower movement than that. The frequency is the same, but the distance is halved. So speed is halved. If the particle's velocity is halved, remember k equals a half mv squared. If the velocity halves, the kinetic energy will drop by a factor of 4 because k is proportional to v squared. You halve this, a half squared is 0.25, isn't it? So therefore, if the kinetic energy is halved, energy is proportional to intensity, so the intensity is halved. So basically, if you halve the amplitude, the intensity drops by a factor of 4. If you double the amplitude, the intensity multiplies by a factor of 4. So this is a true proportionality. Good. Well, I've just rattled through pages 203 to 205. I would like you to watch now the Professor Brian Cox video that I've put a link up on Show My Homework that shows how he sits in a desert, lucky man, and describes an easy way of making an estimate of the power of the sun. Make notes on page 203, 205. Do the purple box work on page 20. Suppose I better show you. So you use the graph to get a series of values, get yourself a table with the distance as a column, I suggest, and use the graph of resistance versus intensity to convert the resistances into intensity values. For example, you get the distance, let's say 30 centimeters from the LDR, and so we are going the resistance is 300 ohms. Well, what's the intensity of light falling on the LDR? 300 ohms. Go to your graph, go to 300 ohms. There it is. Go across, do it accurately, come down here, and we've got an intensity of about 12 watts per meter squared, right? So then you have a series of values for intensity and distance, plot the graph, and from your graph, analyze the graph and check whether the intensity follows an inverse square relationship with distance from the source. It should do. Then do these questions, hand them in to me on Show My Homework, and that's that.